Hi, so this is for Chem 1211. We're going to be covering sections 1.7 and 1.8. And so we're going to be talking about unit conversions and how we write results we get from experiments. When you're taking lab, you will definitely be using a lot of these different units, and you will need to make sure that you know how to report your results when you're measuring something. And so these are our SI-based units. We are measuring things like mass, length, temperature, time, sometimes electric current, depending on what type of chemistry, especially in a Chem 102, you might do, or Chem 1212, you might do a little bit of this. And then quantity of a substance, we're going to be using a measurement called the mole to count amount of particles and molecules and things like that. You need to memorize some of these, not all of these. I'm going to highlight the ones you should memorize. We're going to start here with Tara. I want you to memorize the names and symbols. The names and symbols on one side of your flashcard. So names and symbols on one side. And then on the other side, you should put the exponential. I think that's gonna be the easiest way for you to memorize these. I don't really want you memorizing the numerical values at all. You can, but I would really only look at those for maybe the middle few, because as soon as you get to have a lot of zeros like that, it's going to be really hard to memorize. What we're really looking for is for you to be able to set up the examples. So you see here for the examples, how we would have, for example, kilo means 10 to the 3. So I put kilo on one side of my flashcard and 10 to the 3 on the other side of my flashcard. And so kilo equals 10 to the 3. We can just stick any old unit, SI unit, like gram or meter, after both of those things, and now we have a conversion factor inequality. We could say a kilogram is equal to 10 to the 3 grams. One thing we can also do is we can switch these around. So I want you to think about which of these prefixes are big or small. So we have big prefixes, meaning their exponents are positive, all the way up to deca. And then deci and down, the exponents are negative, so these are small. Want to make sure that we have, and the base unit kind of fits in the middle. So the base unit would be like here. This would just be base. So it would be right in between where it goes from positive to negative would be like just 1. That would be your base. So here we're saying a lot of a base unit equals 1 of a bigger unit. And that makes sense. If I tried to say 10 to the 3 kilograms equals a gram, that would not be true because I'm saying a lot of big things make something smaller. And that doesn't make sense. If for some reason we do need to switch the side of the exponent, we switch the sign of the exponent. So if you need to switch the side of the exponent, you should also switch the sign of the exponent. So that's allowed. You can do that. You may see 10 to the negative 3 kilograms. You may see, so we know a milli is 10 to the negative 3. That was on my flashcard. I could put in milliliter on both sides, put a liter on both sides, and now I have a conversion factor. I could also say 10 to the positive milliliters equals a liter. And let's think about if this makes sense. One small thing equals a small number of bigger things. Yeah, this is a fraction of a liter is equal to a small prefix. This is saying a lot of little things is in a bigger thing, and that also makes sense. But I wouldn't want to say 10 to the negative milliliters is equal to a liter, because this is saying a small number of small things makes a bigger thing. And that doesn't really make any sense, right? So think about what you're doing when you're writing. You're memorizing these, but we're also memorizing them with the intent of writing them like this as equalities. We can use them as conversion factors in our unit conversion practice. So here's a question, and we may do this one in class, but here's a question you can think about answering. So you can pause and think about this one. Answer is B. The rest of them don't really make sense because this is saying kilo is actually 1,000, so 10 to the 3 is equal to 1,000. So we wanted to make that correct, so we would make 1,000 there. That's equal to 10 to the 3. This is saying a big number of meters is in a little nanometer, and that doesn't make sense. If we wanted to fix it, we'd have to put a -9 right here. This one is saying a 10 to the 6, a big number of millis is a meter. Well, that's not necessarily untrue that like a big number of small things makes a meter, but milli is for 10 to the 3, not 10 to the 6. So I showed you this one, the 10 to the 3 millis there. So we can also memorize this milli as 10 to the -3, but if we put the 10 to the 3 next to the milli, we got to change the sign. If you have questions, definitely now is a great time to take a screenshot and text me the screenshot and then ask a question. We're also going to be doing a lot of algebra, so we're going to practice the algebra a little bit with the temperature scales. You will have to memorize this one for sure. And then for the other one, I know for sure in first test I give this to you. I don't think it's on the ACS test, but you may have to use it in like lab or something. I hate the 5/9 and 9 to 5. I use 1.8. So I would say Celsius is equal to Fahrenheit minus 32. I don't have enough space. Divided by 1.8. That's how I would write that. Instead of the 5/9. Or we could write Fahrenheit is equal to Celsius times 1.8, or 9/5 plus 32. Either way, use those conversions or those formulas to see if you could solve this problem. If you, it's best practice to stop the video, try to solve it, then come back. Hopefully you get the answer as D. If not, text me. I can help you figure out what you're doing wrong. All right, when we're talking about measurements, let's say I measure something in the lab and I write down a measurement. Uncertainty is always present. When I'm measuring something with a ruler, I'm guessing that last number that's there. If I use an electronic balance and I write down the mass of something, it's guessing that last number. So uncertainty is always present. It's the last number we record is uncertain. We only want to record that one uncertain number. We don't want to record a bunch of uncertain numbers, right? Because we don't want our whole number to be uncertain. All the numbers, all certain numbers, and the one uncertain number are called significant figures when we're talking about a measurement. And so there are, in each of these measurements, 1, 2, 3, 4, 5 significant figures. Even though there's a 0 here, 1, 2, 3, 4, 5, it's still the last number I wrote. If I didn't, I'm writing this 0 here, and that's going to be recorded as a significant figure. We'll talk about when zeros are not significant a little bit later. Some numbers are exact. So if we count the number of people in the room, that's exact. and that is going to have what we call infinite significant figures. Or actually all exact numbers. Oops, not what I wanted to do. Because if we can think about like counting something, it would be like there are, you know, five donuts. It would be 5.0000000 to infinity. And it would there would be no uncertainty, right? There's no uncertainty. It is exactly that thing. So when we're thinking about measurement, right? All the numbers that we're certain of and uncertain are significant. If we're never uncertain, then we just keep going with those zeros at the end. So we have what we consider to be infinite significant figures, no uncertainty. So counted values and then some conversions are exactly. So for example, 1 inch is exactly 2.54 centimeters. Also definitions. Like a kilometer is 1,000 or 10 to the 3 meters, right? That's definition of kilo. It's exactly 10 to the 3. When we're talking about how many digits to write down when we're doing a measurement, that's based on precision. So significant figures, so how many numbers we write, deals with precision. You might be measuring something, and the way in which you ran your experiment makes that measurement totally not accurate, but you can still measure it to a certain level of precision. So precision is reproducibility of the measurement. So for example, all of these measurements are precise to 4 digits after the decimal. So they all have the same level of precision, and each of the measurements are pretty close together. So when we're thinking about just a list of data, they're pretty precise. Now, these measurements might be totally wrong. Maybe they asked me to measure the length and I measured the mass or something, right? Could be totally inaccurate, but they're precise because they're close together and their level of precision is 4 digits after the decimal. So, but in value, they're close together. So that makes the whole set of them precise to each other, and their level of precision is how many digits after the decimal we're talking about. So let's look at these data real quick. And we sometimes do this in class, but we also may not have time to do this in class. Which student shows precise but not accurate if the actual answer is 122? Pause and then think about it. So if we look for somebody that's precise, it's going to be answers are close together, but not accurate is we don't get 122. It looks like student C is the most precise and the most accurate because they're close to 122 and these numbers are close together. Here in student A, it's not very accurate. It's also not precise. These numbers are not very close together, relatively speaking. Student B, numbers are pretty close together, right? They're only 1 away, and you have a couple of repeaters, but it's not close to 122. So this is precise but not accurate, and what we're looking for here. Answer would be student B. Student D is neither precise nor accurate. These numbers are all over the place, and maybe they might average out close to 122, but these numbers, at no point did we get 122 in any of the measurements. So it would be student B that would probably be the most precise but not accurate. So we're talking about significant figures when we're talking about a level of precision. We want to have as many significant figures as we can. For example, this balance at the top measures 2 digits after the decimal. It could, so it's precise to 2 digits after the decimal versus this balance gives us 4 digits after the decimal. So this one would be more precise. It would give you more significant figures if you were doing measurements with them. So how do you know if a number is significant? All non-zero numbers are always significant. Zeros at the beginning are never significant. Zeros after a decimal point and after a non-zero number are always significant. That's an and there. Zeros at the end with no decimal point may or may not be significant. So what we want to do is, like these zeros here, if they're significant, we would have to put a decimal here to show they're significant, or we could put them in scientific notation without the zeros there to show those zeros don't count. And zeros that are sandwiched between non-zero numbers are always significant. So why don't you pause and answer this question? Which of the measured values or the zeros not significant? So hopefully you paused and you tried it. This zero and this zero are not significant. So not significant, not significant, which means number 1 is an answer. This zero is significant. It's a sandwich. So number 2, not an answer. We're looking for which ones show zeros that are not significant. Number 3, this zero shows up at the end, but it's after a decimal and a non-zero number, or it has a decimal in it and it's after a non-zero. So if you have those two things, the zero counts. So that's not going to be in our answer. These zeros are after, but there's no decimal. So they're after a non-zero, but there's no decimal. If there's no decimal and they're after the non-zero, they're not significant. So that one would count. So answer would be C, 1 and 4. Again, if you have questions, please text me a picture and then ask your question. When you're doing calculations, calculators do not tell us how many significant numbers to put in our answers. When we're rounding, we're going to be applying the significant figure rules we're going to talk about at the end of the calculation. You're either going to round up or leave it alone based on the next number. And we'll do some examples. So with multiplication and division, the smallest number of sig figs in the math equals the number of sig figs in the answer. So if we have this example, how many sig figs are in 0.0340 here? This number has 1, 2, 3 sig figs and 250. Now with the decimal here, this now makes this zero count. So this one also has 3 sig figs. If the decimal is not present, the zero would not count and it would have 2 sig figs. So you see the difference there? So our answer would need to have 3 significant figures because between 3 and 3, 3 is the lowest number of significant figures. So my calculator just gives me 8.5, but I need 3 significant figures, so I'd have to add a 0 there. For addition subtraction, the least precise significant decimal place equals the decimal place of the answer. So this number goes 2 digits after the decimal to the hundredths place. This number goes 1 digit after the decimal to the tenths place. The least precise is the tenths. It goes to the right, the least amount. So my answer has to go to the tenths place. Or 1 digit after the decimal. So I get 129.38, but I need to round it to the tenths place. So I'm going to round it to 129.4 to the tenths place. Practice this, practice these rules, pull up the rules. You have some homework that you can use to practice this, and we'll be doing a lot of significant figures in class. Here's another practice. This is a practice with density. You may want to save this one for later, actually. So let's do that. Let's save this one for later. We'll maybe do this one in class. So I'll go ahead and just take this out of the slides. We'll do this one later in class. That'd be a good recap. I will also do this one in class. Let's make this video a little shorter. All right, when we're doing unit conversions, and there's going to be a lot of this that we also do in class. So delete these. So unit conversions are the basis of how we really are going to be doing math and chemistry. So what you need to know is basically if you have two things that are equal to each other, you can put them on top of each other as a fraction and they essentially equal 1. What do I mean by that? All right, follow me here. Trust me. Can we agree that 3 equals 3? Sure. If I put 3 on top of 3, that equals 1. So if I made a measurement of something and I multiplied it by two things equal to each other as a fraction on top of each other, I haven't changed the measurement. I'm just multiplying it by 1 essentially. So I'm changing the number, but I'm not changing the measurement. So for example, if I measured out a piece of paper and I said, oh, that paper is 11 inches long, but I wanted to tell you what that measurement was in centimeters. I'm not actually going to change the length of the paper to tell you centimeters. What I can do is multiply by a fraction, and that fraction is going to be a conversion factor inequality. This is why I wanted you to learn the SIs as an equality, written as a fraction, and you can write it in two ways. We can write it as 1 inch on top and 2.5 centimeters on the bottom, or I can write 2.54 centimeters on the top and 1 inch on the bottom. Now, which one I use depends on what I'm trying to solve for. If I want to know how many centimeters in my example, I need to cancel out inches. And in order to cancel something out, let's go back up to my little side note up here. If I have something like 2xy over y, the y's would cancel out and I would get simplified to 2x. So if I put two units on top of each other, they cancel out. Same thing here. So if I want the inches to go away, the inches are currently on the top of a fraction. Think about a fraction like that. So I need to put the inches on the bottom. So I'm going to use this conversion, 1 inch on the bottom and the 2.54 centimeters on the top. Now this is going to change my number, like my answer, right? But it's not changing the actual measurement. The paper is still 11 inches long, but 11 inches corresponds to 27.94 centimeters. I'm telling you in a different way, but the length didn't change. So I essentially multiplied it by 1, right? Because two things equal to each other on top of each other equals 1. That's the whole rules of this unit conversion thing. We're going to call it dimensional analysis. Now, if we want to think about significant figures here, there would be 2. So we would have an answer of 2 significant figures. This would be infinite significant figures because it's exact. This specific one is exact. And so we would write our answer as 30 centimeters because I want to count that 0 as significant. I put a dot after. The reason I say, oh, why did I say 30? I'm tired. 28. That was a wild rounding there. I rounded up. I think I rounded just the 1 sig fig. So 2 sig figs, we would look at the 7. To the right of the 7 is a 9. So we're going to round the 7 up to an 8. So 28 centimeters there. My apologies. So dimensional analysis is what I just did. We have our initial units. Units we want is on top. Units we don't want on the bottom. They cancel out. Units that we get at the end. We're going to be doing a lot of practice with this. What I want you to do after this video is go to D2L. You're going to go to the Content tab. And you're going to click on Unit 1. And you're going to click on Dimensional Analysis. practice website. Go to the Learn tab and just let it take you through the Learn tab. Then once you do the Learn tab, you can do more practice. I want you to get comfortable with this. We're going to do some practice in class and the next time I see you.